another episode of Data Skeptic Animal Intelligence. Today we're going to be talking about hacking the colony, or more specifically, how you could be a bit mischievous with an ant colony, I guess, if you wanted to. Becky, have you been exposed to ideas like this in the past?
No, this was actually a little bit new for me. Even as a eusocial insect person, ants are not my specialty. But talking about reasons ants give each other bad information and things like that, that was new to me, and this was really cool. This was fun to listen to.
Yeah, I think everyone knows that ants use pheromones, like, here's the path to the food, here's the path back to the nest. And I guess there's like the death pheromone too. We don't get into the whole taxonomy in this episode, but what we do get into is an interesting modeling exercise that suggests that just a few detractors in the colony could kind of cause havoc and really hack the colony.
Yeah, and that was very interesting to me to think about that in terms of like multiple robots working together and how someone could maliciously attack such a system. That was just something I'd never even thought about before, but it made sense with the ants and using ants as a model for how this could happen. I was like, oh yeah, that all makes sense, and it's very interesting.
In sort of analogous to what our guest today will talk about, their work is in simulation, but apparently in the real world, there are similar phenomenon where ants can get caught in kind of a death spiral where they're all just following each other and everyone starves to death. That makes me think of them as like these wind-up mechanical toys.
Not completely, because certainly if you want to socially engineer people to do really maladaptive things, you can. It might be a little less direct than just a misplaced chemical signal, but I think there's definitely ways you can get most animals to do things like that. But part of the efficiency of having a small nervous system, whether you're an ant or a bee, is to put certain things on autopilot. So even if you can have complex learning, social behaviors, and all this in other contexts, there's still certain things that are on autopilot because your brain can only be so big. Your nervous system can only do so much. So I don't know if I'd say, yes, you're 100% little automatons because you go in a death spiral, but that's obviously not the most cognitively flexible thing they're doing.
Sure. I don't expect ants to emerge as the next intelligent species the way a dolphin or a chimpanzee might.
Fair enough.
And I asked this question during the interview, and they have a pretty good answer for it, but I'm curious to hear your thoughts. All this work is done in simulation, so it's a model. And, of course, the good question is, how well does the model apply to the real world? Now, in their case, they're interested in robotics, so it kind of doesn't matter in the way, a biologist might care about an ant colony. But do you have thoughts on the trade-off of complexity and how you build a model and how applicable it might be to the real world?
I tend to think of like models as what they are. I mean, all models are wrong, and some are just more wrong. I'm sure I'm butchering a quote there, but...
Pretty close. We do the real one in the interview, so we'll save it.
Good. People can hear it. So I think that those models are useful. And if you're doing something like making robotics, you can really control the environment your robots are working in. So I think that kind of modeling is useful. I don't think it's a fool's errand. And then just over time, you can build in complexity and start testing those things in the real world. So I'm all for it. I don't get cold feet thinking about that kind of simulation and modeling.
Yeah, I think there's some super interesting opportunities here for swarm robotics. Like drones have become something that are manufactured pretty cheaply, yet they're pretty powerful. We can attach little cameras to them, and the way computer vision is moving along, there seems to be a really good opportunity for a lot of bio-inspired work to happen in the next decade.
Absolutely.
All right, well, let's jump right into the interview. Thanks to our newest sponsor, math.fashion. Yes, that is a real URL. Visit math.fashion and check out their line of mathematics-themed t-shirts. They sent me the Klein Bottle shirt, which is pretty stylish. I've gotten a few compliments about it, and each one is the opportunity to start a long conversation about two-dimensional manifolds. Get more math in your life, specifically on your body. Visit math.fashion.
My name is Tony Lopez. I'm a PhD student at Worcester Polytechnic Institute, working in the Swarm Robotics Lab.
I'm Aswale. I'm also a PhD candidate from Worcester Polytechnic Institute, and I also work with Carlo Pinciaroli in the NEST lab.
And how did your collaboration first get together?
We took a class together at WPI called Swarm Intelligence, taught by our now advisor, Professor Carlo Pinciaroli. We teamed up for a group project, and it went really well and turned into a paper on disinformation and stigmergic networks that ultimately won a Best Paper award at AMOS, which is a prominent multi-agent systems conference.
And would you mind giving just a high-level definition of swarm intelligence?
If we have to do any task, we can do it in two different ways. We can either have one mega robot that can pretty much do everything, or we can have multiple different robots that work together. The best example is if you have to pick up and place something, you can either have one robot or one system that has capability to do that, or you can have several different things that can contribute towards a bigger cause. So swarm robotics is just that. It's about an emergent behavior from little contributions that every single agent makes.
I think if we ask listeners to think of robotics, not necessarily swarm robotics, but just robotics in general, probably in their mind they're thinking of a monolithic singleton machine that has, all the actuators and sensors and whatnot. Is it true that that is sort of the more popular paradigm, or is swarm intelligence just not as widely known?
That's true. That is common to think of, especially with companies like Boston Dynamics have these very flashy videos of humanoid robots picking up boxes and things. And in fact, our core curriculum initially focuses on armed robotics. It's just a sort of simple introduction. Not that that field isn't complex, but it breaks it down into simple concepts. Swarm robotics is somewhat present in the cultural psyche. I think of like Big Hero 6 with the nanobots. It's obviously like a very fanciful application, but that's an application of swarm robotics. There's all these little robots working together to create something very complex. You might see an application in like a Black Mirror episode, the one with the bees. It's a little scary. We don't do that, but that's another application. Even something like that old movie Twister, where they're sending these little robots up into a tornado to collect data. That's another application of swarm robotics. Anytime you need a lot of robots, they can't be very expensive. They can't be this giant Mars rover. You need to reduce the cost, and so they need to do a lot with a little. We draw a lot of inspiration from biology because nature has had many millions of years to develop ways to execute complex behavior with simple mechanisms. A single ant isn't very smart, but when they work together, they can do pretty intelligent things.
It's interesting you should mention the Mars rover. The first time I encountered the notion of swarm intelligence was this argument, I guess, as they were planning to send those two probes. There was a school of thought, let's say, didn't win, but their thought was, why send two very expensive robots when, space exploration has shown a lot of failure cases? Instead, instead of sending $1 million robots, let's send $1,000,001 robots or something along those lines. Are there other good rationales for why we should prefer or explore swarm intelligence more?
Oh, it's funny that you pointed that out because that exactly is the current research problem that Tony and I both are currently working on. If you send one mega robot and for some reason, let's say its wheel came off, you can't conduct any of the experiments. But if you send six robots, one of those fall off or one of those gets out of commission, you can still use many of the other robots that you have. So there is a benefit of redundancy. And that just not have to do with one specific robot. Both Mars and Moon and the other planet systems are really notorious for the regolith that they have, which is their sand is as sharp as glass particles. So that really eats through the sensors and the tools that they have. So more sensors and more tools that you have, better it is for your system. One of the things that we also discuss is if you have to put multiple sensors on one single robot, you also have to think of their intercompatibility, how they all come together on a robot, how their mechanical system should be compatible with each other, and all those things. If you can break down them into smaller little parts of problem, your overall problem becomes much more simpler. Both Tony and I are currently conducting research on if you have to send a fleet of robots on, let's say, Moon, and then they have to conduct their tasks together. how should they manage together, which robot should have which sensors and tools, given that you have all the necessary requirements, who should do what kind of things. So these kind of calculations, optimizations. So our current research involves just around that.
Well, I presume in most research, swarm intelligence explores collaborative situations in which you have multiple robots or multiple agents that all share a common goal, maybe even if they've, subdivided it in different ways. But what's sort of not obvious is how they communicate, or do they do centralized planning or distributed planning, or what are some of the challenges about deploying such a fleet?
You again mentioned the one of the biggest problems that you have. If you have, let's say, 10 robots, and moon is big, you have craters and you also have valleys. If one robot drops out of communication, how do you know what that robot is planning? So you can have a centralized computing system, which is a station which can calculate everything, compute everything, and just distribute the order that each robot has to follow. Or in the decentralized system, where each robot can compute their own system, and then they communicate among themselves and then come to the most mutually beneficial solutions that they all have. So yes, centralization, decentralization is a big part of our problems.
To the question of how, there's a few different algorithms that can manage this sort of decentralized communication. One that comes to mind and that we look at in the swarm intelligence course was an algorithm by, I think his name is Steven Strogatz, and he looked at fireflies, again drawing inspiration from biology. I don't know if you've ever seen a big group of fireflies, but they all start that blinking, and they manage to blink synchronously. It's like a whole array of fireflies blinking together, and obviously there's not some central coordinator, and also none of them can see all of them together. None of them can see the entire swarm. With a lot of math, you can come up with a way of syncing them up. That algorithm uses what are called coupled oscillators with a phase shift, where they have a sort of internal counter, and they're sort of adjusting the expectation of when the next blink will be of their neighbors. Without going too much into it, it suffices to say there are ways of doing the decentralized communication, and that is sort of preferred for us. Maybe early on in our experiments, in the simulations, we'll do a centralized computation just for ease of use, but it's usually, I don't want to say trivial, but straightforward to adapt that to a more decentralized form of communication.
So, of course, if we're building robotics, in theory, they could have Wi Fi and communicate that way. But when we look to be a little bit more bio inspired, could you talk about some of the novel ways that animals communicate that you've been interested in?
The animals can communicate in different ways. So, like birds talk with their bird calls, bees can communicate via dancing. And what our research talks about is the ants communicate using a mechanism called stigmergy. Now, what stigmergy is they modify their environment a little bit to leave the cues for the other ants to follow. An intuitive example that we usually talk about is if you have to go on a hike, every hiker can leave a pile of rocks or some a colored flag to inform other hikers that may be following him that this is the path that I follow and this is the path that may lead you to something. They secrete a specific chemical called what we call that as pheromone, and that can leave a trail that that specific ant is following. So let's say if an ant is leaving from his nest and is trying to go out, it needs to come back home. And that's why when it is leaving home, it starts leaving a pheromone specific to leading the path back home. So that if it has to come back, all that it needs to do is follow its own trail back to the nest.
Right. Stigmergy is just a fancy word we use for communicating through the physical environment instead of communicating directly to each other.
Yet the physical environment evolves on its own. In the case of pheromones, which I guess are scent based, when I think of scents, I think of things that are, falling off. The strength declines with time. How do you model stigmergy?
Yeah, that you sort of hit the nail on the head there. That a crucial part of stigmergy is this idea of evaporation, where the old trail fades over time. In a sense, you can still keep up with that metaphor of the hiking trail. If a trail hasn't been traveled in a long time, it might start to get more overgrown and disappear, so to speak, so that the more frequently traveled trails get reinforced because people keep stomping down the grass and clearing the way. With the pheromones, which are scents, basically, the ants can smell this. It does evaporate over time, so that the intensity of the smell when it's fresh is easy to follow. But if it's been a while, then it's negligible. It's evaporated into the air.
Should we look at that as a bug or a feature of the communication?
I think it's really important in enabling this sort of communication, because without it, if the trails didn't fade, there would be no way of knowing what the up-to-date trail is. And so the whole mechanism kind of wouldn't work. In our paper, we messed with the evaporation rate to see how the changing evaporation rate would impact the system as a whole. We reference a couple of applications of this, in the real world. In reality, it's kind of hard to model this because we don't have a lot of physical materials over which we can control the evaporation rate. We can lay down some sort of crystal that will decay over time, but ideally we would be able to control the rate of the decay. And so that's one reason why this mechanism, while powerful and effective and scalable, which is super great for something to be scalable, it's not commonly applied in real world applications.
So if we stick for a moment to the biology side, I expect most listeners will be aware that ants leave pheromone trails to food. Is that the whole story, or is there more to it we should know?
Yes, there definitely is a little bit more to that, because the ants are ants have just evolved to follow the trail. There has been research that mentions that they cannot avoid a specific pheromone. There was an experiment in which there was a white tube, so one ant can go in straight, and then it encounters a two path fork. On the left, it had given some bitter solution, and on the right it had given some sweet solution, and they had some specific pheromone to it. And what they had found out was the ant can just ignore that there is pheromone, but they cannot evolutionarily learn that this specific type of pheromone is harmful and I should not follow it. So they just cannot do that. So what we asked is, what if we try to take an advantage of that? One of the ideas that we discuss in the paper is, some of the ants are just malicious. Now, when I say malicious, whatever that we will discuss, this same mechanism can also be triggered even if you have a malfunctioning ant. Anyway, so what we introduce is a small fraction of colony as detractors, which is basically a malicious ant. And what that does is it leaves out a fake food pheromone trail. So even if there is no food to be found, it will still start leaving out a food pheromone trail so that the other ants can be fooled by it. That's how it can deter the normal ants, the benevolent ants, from actually going out and foraging food and finding food, because they are just too busy finding this fake trail that doesn't really lead anywhere.
And using our hiking metaphor, this would be like a rogue hiker walking around the environment randomly, piling up rocks, creating these cairns that don't lead anywhere. And in doing so, messes up the whole system because the other hikers don't know what to follow. They inherently trust the markers, the trail markers. But if someone is sabotaging that, whether it's through malfunction or sabotage, the system falls apart. And that was the core conclusion of our paper, was that this mechanism is fragile.
Well, I definitely want to come back to the detractors and the fragility of it all, but for the moment, if we could just champion the ant colony optimization technique, obviously ants have survived for quite some time. I'm sure nature messes with their trails a bit. The wind could blow the pheromone, or soil could shift. Presumably, this approach is somewhat robust to the activity of the distractor. What would we hope would happen if we really wanted to stick to the standard ant algorithm? How should it work itself out?
So, is your question specifically regarding if we are implementing ant colony optimization?
Well, I guess it's this. So if we take the detractors off the table for the moment, let's just say we have a lab set up with some ants, and we put a fan over it, or we once in a while took a rake and just kind of moved the soil around. Certainly, that would harm the colony, but I don't think it would utterly collapse it. Or perhaps you would tell me it would. In what ways, I guess, would it be robust? Would these systems be robust to those sorts of changes when there's no detractor present? Do they work themselves out normally?
Yeah, there's a bit of a difference when the markers are removed versus when the markers are, when fake markers are introduced. When the markers are removed, it kind of just means the ants need to start over, versus when fake markers are present, there's no real, I mean, we propose one countermeasure, but it's not straightforward what you do. And I keep going back to this hiker metaphor just because it's easy to visualize. But if someone went and removed all the cairns, it would just mean hikers need to start over, but they wouldn't be led to their doom, so to speak, by following fake trails.
Can one detractor collapse the colony, or do you need a certain fleet of them?
Our simulations showed that if just 3% of the colony were detractors, then nobody would find food and the entire colony would starve. Just 3% was enough to catastrophically fail. But even less than that, 0.3%, as I recall, reduced food collection by 50%.
Could you talk about the modeling and the experimental setup?
What we do is we just have a simulation of ants in which we try to replicate how ants forage food, which is at the center. We just have a nest, and somewhere in the simulation, we put a block of food. At the start of simulation, the ants continuously leave the home pheromone food, which is basically the way that they need to follow to get back to the home. When the ant is currently moving, this pheromone is continuously getting evaporated, and simultaneously the strength of pheromone that the ant secrete also degrades. It takes advantage of both of that, so evaporation and the decreasing concentration of the pheromone secretion to lead the way back to the nest. So that is how whenever an ant starts from the nest, it keeps track of where the nest is. While exploring, if it finds food, then it changes its mode to food mode, which is basically I have found food, I am carrying food. And when it is carrying food, instead of leaving the home pheromone, because now it needs to just follow the home pheromone, right? So then it secretes the food pheromone, which is I have found food, and if you follow my this trail, you might also get to the food. Again, it follows the very same two things. It starts with the highest concentration of that food pheromone, and as it walks along, the pheromone secretion concentration decreases a bit, and at the same time, the pheromone also evaporates. So the other ants will just, if it encounters the path of food pheromone, it will try to chase a direction in which the concentration is higher. That way leads to the food. And that's how, even if one ant finds food, all the other ants will also around that particular belt will get drawn into the food region. And as more and more ants follow the same trail, the food pheromone trail gets thicker and thicker. It just gets reinforced by all of these other ants which are walking the same line. And that's how the ants usually find food in the simulation, that is.
Well, when everything's working, I guess that does work out for the ants. Could you describe how the detractor decides to lay the false trails?
In our initial paper, the detractors simply always lay food pheromone, whether or not they've found food. They're just always laying down this food pheromone. So otherwise, they act exactly like all the other ants. They follow food pheromone when they're looking for food, and they follow the home pheromone when they're trying to find the nest. They are not particularly intelligent, or coordinated. And we did that on purpose because we wanted to make only a small change so as not to create like a super ant where it just wasn't fair. So for example, you could say, well, our super detractor ant can lay pheromone that's 10 times as potent as the other pheromone and never evaporates. Of course that would destroy things, but it's not as interesting as just a single little tweak. That all it took was that little tweak of we're going to lay food pheromone no matter what.
So would it be correct to say your detractor ants are not so much devious as they are defective?
Yeah, it could be a malfunction. That's one explanation. One of the things I asked our advisor at the beginning of this is, I don't understand why ants would lie this way. And his response was, ants wouldn't lie, but robots would, because people program robots. So whether or not it's a malfunction or an intentional act of sabotage, it still has the same effect.
And I'd love to dive a little deeper into the modeling. What does an ant look like when you encode it mathematically?
We didn't write the simulation from the ground. There is an existing simulation of ants that we find, but that simulation was just to replicate how the normal ants behave. We just modified that. We didn't write the simulation. So the ant in the simulation is just a vector of two numbers, which is its x and y coordinate. However, the floor is a grid. So you can imagine that as a floor is made up of tiles, thousands and thousands of grid of tiles, whereas an ant is a single dot moving on those floors. If you are at any given point, that specific ant will be in any one box of a grid or a tile of a grid. So the world is a grid system, whereas the motion of ant is continuous. So the motion of ant does not really have to move in a Euclidean format, which is go straight or go right. It can do any degree of turns. It can move just like an ant.
There's a famous quote, often misattributed to George Box, that says, all models are wrong, but some are useful. On a scale from wrong to useful, where do you see your simulation?
That's a great quote. We have chosen this simulator not because it was correct or biologically accurate, but because that is how we usually create robots. The robots' movements are continuous. However, their perception of the world may not be. We found that this specific model of ant movement was closely resembling how we usually model robots, and that's why we went to it. So I would say it's more to the spectrum of useful.
And if I were to put on my most, I guess, skeptical, pragmatic glasses, and I was looking at this and saying, oh, geez, this research shows that with just 3% detractors, the colony will collapse. Maybe we shouldn't invest in swarm intelligence. How would you talk that person down off the ledge?
I think what garnered our paper a lot of attention was that we didn't just point out how this mechanism was fragile, but we proposed one way of countering it. So imagine a hiker's following a trail, but they're carrying a can of yellow spray paint. If they are walking for too long and they don't find the end of the trail, they start spraying the trail in yellow and saying, this is suspicious. I've been walking for a long time following these cairns and I haven't found where I'm going. And so now that this trail has been marked yellow, if another hiker sees this trail that's marked in yellow, they'll avoid it because other hikers have marked it as suspicious. To answer your question, like with any application, you would have to build in safeguards. In fact, one of the things we look at when we're doing research, the first question is, okay, how can we break this? How can we make this algorithm not work? And then we think about how to fix that.
It also exposes some of the vulnerabilities that we may have in system, so that if you go on and invest in a system that replicates ant, you should be aware that this flaw exists and this might be the possible defense. It just improves the current level of understanding of we have of the system.
And in terms of the collapse or the starvation of the colony, I understand that's the result of the simulation, and it's at least in part due to the misinformation that the detractors are laying down. But is there anything to expand on related to that? What ultimately seals the fate of the colony?
This can happen even in nature. You can find videos of this on YouTube, called it a death spiral, where the ants just start following each other's trails and they just follow each other in a circle endlessly. That sort of behavior is what we observed in our simulation when all these fake trails were put down. And that's why just ants stopped exploring, because they got hoodwinked into thinking that somebody found food, and they just kept following it.
So it does exist in nature. Would you say it's prevalent or a rare case?
Again, we're not biologists, so take this with a grain of salt, but I think it is the exception rather than the rule.
However, it is also one of the nature of some species of ants. So there is this species of ants called polyergus, and they specialize in enslaving the other species of ants. They raid a specific a colony of ants, and they start spreading this what they call propaganda pheromone, which just spreads panic in the colony. These ants take advantage of that panic, go in and steal their larvae, take these larvae back to their own nests, and when these larvae hatch, they just have been brought up in this colony of polyergus, so they just assume themselves as a slave. So it's not really a slave because they do that on their own, because they have been brought up in that. But yes, so it does not this exact thing that we discuss, but such kind of taking disadvantage of this pheromone does exist in nature.
And in terms of the proposed defense of it that we touched on earlier, how effective is that in practice, or at least in simulation?
It depends on how you define the success. In the paper, we define two parameters to gauge how the colony is doing. First is how much food do you bring back to the nest, and second is how much of your colony is actively contributing towards foraging part. And the reason that they both are important is, let's say in an ideal scenario where detractors don't really exist, eventually every ant will end up bringing food back to the nest, and they will bring back as much food as they can. However, in case of detractors, two things can happen. First is the detractors might be able to fool a certain fraction of the colony, so other fraction still actively functions and brings back food. And second is, irrespective of how much fraction of the colony is fooled, the total amount of food that the colony was able to harvest or bring back to the nest, that was hampered. So, for both of these two different parameters, we found out that when the defense mechanism that Tony explained a few minutes ago, which was that the ants start to leave out what we call a cautionary pheromone, which is something is not right with this path. So, when we deploy that, for most of the cases, and what I mean by most of the cases is you can also use different parameters for this defense mechanism. All of the colony eventually contributes towards the bringing back of the food. However, the amount of food that is collected still is little bit impacted. So in some units which don't really make sense in human terms, because it was just a simulation, in normal situation when the ants were able to collect 21 units of food, in this specific defense mechanism the best that they could get is just 9 units. So they are still doing good, but not as great as without detractors. But the point that I would like to mention out here is, in presence of detractors, that value was as low as 0.01. So it went from collecting almost no food to half of the food.
But still effective, yeah? I mean, a way to defend oneself.
And that was one of the conclusion of the paper that we have, which is it is effective, it brings back something, but it is not a silver bullet to the problem. The problem still persists, but it is just a minimization of the impact that you may have.
And it was just one idea we had. There are other possible ways to address it, but it was enough for us to say it's possible to do something about this.
And what are each of you working on currently?
Both of us, Tony and I, are currently working on multi-robot task allocation. let's say if you have multiple robots, each with a specific set of sensors and tools, and you need to conduct a specific experiments for which you need a set of specific sensors and tools. So what I specifically work on is creating schedule for each and every robot. For example, a robot A must be at experiment number 3 by 2 o'clock, and it needs other robots for the experiment to complete. And every robot has their own schedule. This schedule is made for like in a decentralized way, which is every robot thinks for itself. So that's what I work on.
The sort of common thread that our lab is working on right now is fault detection. In the case of the ants, it would be what can we do about this ant that has a fault? But that thread connects a lot of our work. Swarms are by one general advantage of swarms is that they're robust, but that's not a given. So we do need to build that in. What Ashay was talking about with the scheduling, I like to think in metaphors, and this is like a simple example, but might help people visualize the problem a little bit. Is imagine that there's like a warehouse, like Amazon has this warehouse with a bunch of boxes, and some are heavy and some are like high up, and maybe you have a robot that can lift a very heavy box, but it doesn't have long arms, and another robot has really long arms, can reach a high box, but can't lift a heavy one at height. And then you might have a more expensive one that can do both. And so what Ashay's work is saying, all right, I have these robots. Some are strong, some are long, strong. And I have this task, like all these boxes that I need. What's the quickest way or the most efficient way to send everybody out and get all those boxes in record time? And that's just an example. It could be like moon robots. Like one robot knows how to drill a hole, another knows how to collect a sample, another knows how to like scout a location. Same general idea. You have these tasks in these various locations. So Ashay, his swarm is set. These are the robots you have in your fleet, and then what's the most efficient way to go get everything? What I'm looking at is what if the swarm isn't set? It's called co-design, where you're designing the hardware in tandem with the task. So I'm saying, what if you can pick? How can I get the best bang for the buck? Where I'm designing, I'm saying, all right, you only need one of these super robots, one strong, long robot, and the rest can be these specialists. And you can do as good a job as if the whole fleet was super robots. That's what I'm looking at. I'm looking at, how can you achieve efficiency through custom designing the swarm? And that does have very practical applications, like space exploration we talked about, where every little kilogram that you put on that rocket matters because it's very expensive.
And where do you both see the field going in the next 5 to 10 years?
I pretty much believe that most of the future that we are currently looking into are multi-robot stuff, because making one mega robot is much more technologically, economically expensive than making multiple smaller robots. You just can get a lot of stuff done in equal amount of time. For example, if you have to, let's say, map a certain region on, let's say, moon, if you send one robot, even if that one robot is going at its maximum capabilities, it can only map and encounter a certain region. Whereas if you have three little robots, that can cover a lot more area in the equal amount of time. So there are several advantages of preferring multiple robots rather than one large one or a one super robot. I do believe that industry is currently looking into just getting into a lot of little robots, so multi-robot systems.
In the case of the Mars rovers, the most recent mission, we sent a drone as well, right? So this is a little multi-agent system, and it's a good example of the rover can do a lot, but the other guy can fly, which is a sort of specialization that enables a lot of different types of missions. The work that we're doing will have a strong impact in efficiencies. And once you have those efficiencies, you can do some really cool stuff. And it's stuff here on Earth too. Like imagine a fleet of robots that could start to repair a coral reef, or a fleet of robots that can search for survivors after a natural disaster, or can monitor the spread of a wildfire and direct, first responders to the areas where they can have the most impact. I don't think I'm exaggerating when I'm saying that this technology could save lives.
What's next for both of you?
I'm currently in the process of finishing up my PhD. I'm currently looking for jobs starting in Jan. So yeah, you can find me at LinkedIn, Ashay Aswale, the same name as you may see. And yeah, thank you for hosting us.
I have still a little bit of time left in my PhD, but I'll nonetheless be looking for internships. If there are any companies out there that can use this sort of work in multi-agent systems, it has a lot of different applications that can be relevant to various industries. These optimization problems really have a role to play almost everywhere. So you can reach me at alopez3@wpi.edu.
Well, I want to thank you both for taking the time to come on and share your work.
Thank you for having us.
I'm glad to join. Thank you.